A logic gate operates as a device performing Boolean functions, executing logical operations on binary inputs to produce a single binary output. These gates can be implemented through various means like diodes, transistors functioning as electronic switches, or more commonly with MOSFETs. They are integral components of logic circuits, found in systems ranging from basic multiplexers to intricate microprocessors containing millions of logic gates. Moreover, compound logic gates like AND/OR invert and OR AND invert are widely used due to the simplification and efficiency gained by combining multiple gates. The historical development of logic gates can be traced back to the refinement of the binary system by Gottfried Wilhelm Leibniz, the mechanical logic gates in Charles Babbage's analytical engine, and the groundbreaking work on switching circuit theory by engineers like Claude Shannon and Akira Nakashima in the early 20th century. Such advances laid the foundation for modern digital circuit design, with milestones like the insulated gate transistor patent in 1948 by Bardeen and Bratton, leading to the formation of CMOS technology. Different types of logic gates such as AND, OR, NAND, NOR, XOR, and XNOR are represented using standardized symbols defined by industry standards like IEE and IEC. These symbols serve as a universal method for describing complex logic functions within digital circuits, ranging from simple gates to complex systems like microprocessors. The symbols have evolved over time, adapting to advancements in circuit design methodologies, from traditional schematics to modern hardware description languages like Verilog and VHDL used in designing custom integrated circuits and programmable gate arrays today. The application of De Morgan's laws establishes an equivalence between AND and OR functions with inverted inputs and outputs. Similarly, NAND gates are analogous to OR gates with reversed inputs, while NOR gates are the counterparts of AND gates with negated inputs. By adopting alternative symbols for basic gates that depict the opposite core concept, AND or OR, with negated inputs and outputs, logic circuit diagrams become clearer. This approach helps in identifying accidental connections between an active high output and an active low input. The use of these alternative symbols facilitates the replacement of connections involving negations at both ends with a negationless link and an appropriate gate adjustment. Moreover, connections featuring a negation at one end and none at the other can be better interpreted by employing the De Morgan equivalent symbol at either end. When both ends of a connection exhibit negations or polarities, the absence of logic negation in that path simplifies the logic state's transition between symbols. It is crucial not to solely associate shapes with OR or in functions, but also consider the bubbles at inputs and outputs to accurately determine the actual logic function indicated. De Morgan symbols offer a clearer representation of a gate's primary logical purpose and the polarity of its nodes in the signaled state. For instance, in a scenario where a two-input NAND gate triggers a motor when one of its inputs is grounded by a switch, the De Morgan symbol of a two-negative input OR gate correctly illustrates the relevant logic of an OR gate. This differs from the regular NAND symbol, which implies AND logic. While the standard NAND symbol portrays a bubble at the output and none at the inputs, contrary to the states activating the motor, the De Morgan symbol showcases both inputs and output in the polarity required to operate the motor. De Morgan's theorem is frequently utilized to construct logic gates solely using NAND gates or NOR gates, primarily for cost efficiency reasons. In implementing logic gates, De Morgan's laws play a crucial role in simplifying circuit diagrams and ensuring accurate interpretation of logic functions.